All right, welcome back, everyone. Today, Maryanthe will continue her lecture series on learning from complexity.
Great. Okay, so thanks everybody. So in lecture one, we saw a little bit about how thinking about model theoretic ideas and very, very large, not in the technical sense, but very large cardinals could perhaps give some insight into the finite. And maybe a theme of today's lecture is how if you look at very large sizes from a model theoretic point of view, you can say something about, the merely large things, about perhaps the around the continuum. So, okay, so what I'll talk about today is essentially in this paper with Shelah cofinality spectrum theorems and model theory, set theory, and general topology. So this is part of a series of papers we were writing on Keisler's order, which I will say something about in due course. Okay, so there will be several different themes in today's lecture, so we can think about them as slightly different chapters. So the first one is cardinal invariants of the continuum. Cardinal invariants of the continuum. Okay, so I want to start by telling you a little bit about what these are, how they work, and these are going to give us different ways of measuring the continuum. So give various ways of measuring continuum. All right. So we know from Cantor that there are different sizes of infinity, right? So we have not the first infinite size, the size of the natural numbers. This is strictly less than 2 to the aleph naught, which is the size of the reals. Okay, so how far apart are they? So Hilbert, so let me write Cantor. Okay, so Hilbert's first problem asks about the continuum hypothesis. Is aleph 1 equal to 2 to the aleph naught? So is the size of the reals the next biggest infinite size than the size of the natural numbers, or is there something in between? So how would you think about trying to measure this? So, okay, so first there's a general disclaimer, which is that I'm speaking as a model theorist and set theorist and general topologist. So this part of the talk is in, let's say, set theory, general topology. So, all right, so how might you think about this? So a beautiful idea of how to think about studying this problem in the first half of the 20th century that was very productive both before and after Cohen's work in inventing forcing was to try to think about externally defined sizes that you could show fit somewhere in here. So you're asking about the conjecturally non-empty region between aleph 1 and 2 to the aleph naught. If the continuum hypothesis holds, there's no space, but maybe there's some space in between. So let's try to define different sizes that we can show fit in here, and then try to think about their relationship. So let me give you an example. So an example that's easy to describe is E, the bounding number. So these things I'm describing have a long history in the 20th century. The names, for the most part, I think were given by a person called Van Dalen, who wrote a very nice article in the much later, maybe in the 80s, called The Integers in Topology, but and went back and gave the history. But we'll use the modern name B, the bounding number. So this is the smallest size of an unbounded, say what this means, family G of functions from natural numbers and natural numbers. Okay, so what does this mean? So if you have, so in this talk, star is always going to mean up to finite error. So f less than or equal to star G means that G is bigger than f on all but finally many values. So a family G is bounded if there is some f from natural numbers to natural numbers so that f, let's say, is strictly, we can do strictly greater than or equal to g for all but finitely many values for each g and g. Okay, so maybe after the first value, it's bigger than the first one, and after the first two, it's bigger than the second one, and so on. So how big does a family of functions from natural numbers to natural numbers need to be before, before it's unbounded? So what's the smallest size of an unbounded family? Okay, so first observation is that whatever b is, it's no bigger than continuum because that's the size of the family of all functions from natural numbers to natural numbers. So once you have all possible functions, that's an unbounded family. What about in the other direction? Okay, what about, can we show it's greater than or equal to L of 1? So the way we're going to show that is we're going to show it can't be countable, can't be finite or countable. So suppose I had a family G, which was countable. So suppose we had G, which is, Gn less than omega, we had countably many functions, then we would just list them and we would diagonalize to build a function that bounded them. So f would be bigger than G1 on 1, bigger than, G1 plus G2 on 2, and so on. And since there are only countably many of them, we can build a diagonal element and we can get a bound. Okay, so any questions about this?
I understand. Why in the continuum, if you take f to be any, for n, anything smaller than n, you have so many possibilities. So is there an equivalence? Is it totally ordered?
Oh, okay. So let me see if I've, okay, so I have G, which is a family of functions from, so G is a family of functions from natural numbers to natural numbers. And G is bounded if there is some f, also a function from natural numbers to natural numbers, such that for every G and G, f is greater than G at all but finite values. So this means the set of n in n, where f of n is less than G of n, is finite.
So far, I could take as bounded G all functions with value in 0 and 1.
Sorry, say again?
Taking for G the set of all f with value in 0 and 1.
Yes.
So that's the continuous. Continuum, that's all subset of n.
Yes. But I'm asking about what's the smallest size of a family, which is unbounded.
Oh.
Yes, okay. So there could be lots and lots of families that are bounded, lots and lots of families that are unbounded. I'm certainly not claiming that there's a particular size with a property that once you're that size, you have to be bounded or unbounded. I'm just asking, so maybe this is in some ways the complement of what you're saying. So being unbounded is hard if you're small, right? You have to spread out the functions a lot. So this is saying that if the family of functions is countable, there's no way you can spread them out to be unbounded because you can always diagonalize and find a bound.
Okay.
Okay, great. But the 0 and 1 is the 0 and 1 is a very nice example. I'll try to say, okay, I may say something about P between 0 and 1 later. Yes. Okay, great. Thanks. More questions. Okay, so what this tells us is that whatever this number is, so this is some externally defined number, some family of functions with smallest size of a family of functions with this property, whatever it is, it's at least L of 1, it's less than or equal to continuum. And so the project of cardinal invariance of the continuum is to define lots of other numbers, right? Lots of other externally defined sizes like this. You could ask, bi-appeal to anything that you could prove would actually generate something in this interval. And then if you didn't know anything about the resolution of the continuum hypothesis, maybe you would start to think about this region by comparing these different sizes. And so if you actually could prove that two of them were distinct in CFC, then you would have solved the continuum hypothesis. But actually, as I understand it, so the way it happened was the people before the invention of forcing had this great intuition and proved basically everything they could prove in ZFC. And then there were lots of inequalities that were left open. And then after Cohen shows that the value of the continuum of Gödel and Cohen is independent of CFC, then cardinal invariants of the continuum actually become really important, because now if you want to make the continuum different sizes via forcing and understand what the consequences are of those different sizes, these give you a way of telling you much more precisely what properties are true in all the different models you build. So now I built a model where the continuum is really big, and B is this value, and D is this value, and P is this value, and T is this value, and that tells you something about the shape and the size of the model you built. So this is a very active area, and people continue to define many cardinal invariants. But the heroes of our story, so P and T, so this will be the pseudo-intersection number and power number. So these are two of the classical cardinal invariants, and the question of, so I'll tell you what they are in a minute, but the question of, there's one inequality that's obvious, and then the question of whether or not they're equal had remained open for a long time and became, I guess, more and more interesting the longer it remained open. So, all right, so here's some notations. So so when I write this, I mean countable subsets of natural numbers. I could say infinite subsets of natural numbers, because this is the only size available to us. All right, so P is the smallest size of a family of infinite subsets of natural numbers with two properties. So the first property is, if you take finitely many of them, they have infinite intersection. Now, I should really say finitely many and at least one. Okay, so I don't know what an empty intersection is, an intersection of zero of them. But okay, so strong finite intersection property, the intersection of any finitely many, but at least one finitely many elements of F is infinite. Okay, so in that sense, they have a strong compatibility condition, but they also have no pseudo-intersection. So they aren't too compatible. So what does this mean? This means there is no infinite A subset of n, so that A is contained up to finite error in each element of the family for each B and
That's very close to BC diamond.
in what sense?
If F, for example, was closed under intersection, then the first condition basically is about chattering.
Mhm.
And the size of F doesn't change if I add the complement.
Yeah, so it's an interesting, I mean, in some sense, filters in VC dimension are very close. And so, yeah, that's a nice point. So you have this strong compatibility condition, but you're far away from having a common intersection. So just to make this point a little bit more strongly, let me give you a non-example. Okay, so non-example, by which I mean it will satisfy one condition and not the other. So take all cofinite subsets of natural numbers. Okay, so all of them are infinite, so they satisfy this condition. The intersection of any finitely many is infinite, so they satisfy this condition. They don't have an intersection, right? There's no set or there's no infinite set, in fact, no set at all that is in the common intersection of all cofinite subsets of n. But is there a pseudo intersection? So is there an infinite set which is almost contained in all of them? Audience?
Everything.
Yes, exactly. Natural numbers. So they have a pseudo intersection. So in itself, right? Great. Okay, so this might suggest that if you're going to find an example of P, the smallest size of a family with these properties, that it shouldn't be countable. It requires slightly more of a proof. So this is due to Hausdorff. Not this example, but the general proof of P is very political. So I think that's P36. Okay. Any questions? There were
I was
surprises.
very interested in cardinalities.
So there were lots of interesting questions about the reals, questions about subsets of the reals, questions about, if you want to try to understand what the reals look like and what their sizes are. I mean, I think, so general topology had many connections to things. I think, yes, okay. Maybe I can say more later, but so what is the tower number? So it's very close to P. So P tower number. Okay, so it's again smallest size of the family F of infinite subsets of natural numbers. And the first condition is it's well ordered by reversed almost inclusion. So containment up to finite error. You could also say linearly ordered because you're looking for the smallest size. So that will end up being well ordered. And you ask for no pseudo intersection. So let's just compare. So if you have a family of sets and they're well ordered by reverse almost inclusion, then anytime you have finitely many of them, then their intersection is going to be infinite. So you'll get SF by P for free. So anytime you have a family witnessing the tower number, then you already have a family witnessing P, and so P is less very clear.
You told me that all elements of the family are infinite.
Yes. Yes. So if you want to think about a non-example for this, right, you could think about exponential segments. So natural stuff. So again, that will not satisfy the condition of having no pseudo intersection. But if you think about the two non-examples side by side, the family of all cofinite subsets of n versus the family of coinitial segments of n, in both cases, right, there's the question of whether or not you have a pseudo intersection, but you might imagine that if you were allowed to spread out the sets, you didn't force them, you didn't require them to be well ordered, but you allowed them to spread out somehow, that maybe you could do it with a smaller family. So to say something, I'll just make a comment about binary sequences. So where can I draw this? Maybe I'll go over here. So
Leave the other one.
which other one? Is there one in?
Both behind you.
All right.
This one you cannot.
Okay. Then this will just be an aside. Okay, we have a moment for an aside. A less misleading example. So I'm going to give you an example of, just because the binary sequences came up, of a set of functions which satisfies the condition. So it's going to satisfy any finitely many have infinite intersection, and it's going to satisfy that there's no pseudo intersection. It might not be a witness to P because it might not be the smallest size of such a family. But just to see how these things arise in nature. So I need to find a family of infinite subsets of natural numbers, but I can identify the natural numbers with any other countable set. So why don't I identify them with the internal nodes of a binary tree? So I have a binary tree. Number of nodes is countable. So I think about this as my set of natural numbers, and the number of branches and size continuum. Right? So for every possible branch, row, I could look at a row, which is the nodes on this branch.
Or is that an infinite binary tree?
Yes, countable height, infinite binary tree. So the nodes are the finite binary sequences, finite sequences of zeros and ones, and the branches are countably infinite ones. Okay, so look at the family of sets that are along each branch. So any two of them have finite intersection. If I look at the complements, the C rows, so C row is the complement in the tree. And B row, the C rows have the property that any two of them or any infinitely many of them have, any two of them or any finitely many of them have infinite intersection, right? So these guys are almost disjoint. Any two of them have finite intersection, but the complements have SFIP. Any finitely many of them have empty intersection. Now, is there a pseudo intersection? So if you look at the tree, you have this.
So what is row?
Row is a branch.
Just one branch.
Just one branch. For each particular row, I could look at a set, which is the set of things along a branch. And so, right, so this family of continuum many things, any two of them have finite intersection. The complements have this SFIP. Now, it isn't quite witnessing P because I still have this issue of the pseudo intersection, and I can see that by looking at the B's. So the B's are almost disjoint, any two of them have finite intersection, but I could find other sets that also intersect all of the B rows and finitely many, right, and finitely many points. For example, take, the set of points just off a path. So this is an almost disjoint family, but not a maximal almost disjoint family. And if I were to take a set like this that intersects each of these infinitely many, then its complement would be a pseudo intersection for this. So if I could make this a maximal almost disjoint family, which you can do by Zorn's lemma, then this would be a family which witnesses SFIP and no pseudo intersection. So that's one way to get such a family. Okay.
So you need Zorn's lemma to get an example?
Just to get this example. So this is just to say it exists. I mean, the bounding number, it was clear you could get them, but here it's just a way to see this exist. Okay, so this is what I wanted to say about the cardinal invariance of the continuum. And so, perhaps I should also say we have these P and T's, this P and T. So P and T and so all of 1 is less than or equal to P is less than or equal to T, actually is less than or equal to B. The bounding number we talked about is less than or equal to continuum. And so we said this was Hausdorff. This is clear. This we just showed. This was Rothberger. And Fourier. And Rothberger also showed in our language that in the smallest possible value P can take, if P is equal to Aleph1, then T is equal to Aleph1, 2. So in the smallest possible value they can take, there they have to be equal. So this begs the question of whether they are equal. And again, this gets mentioned over the years. And so, all right, so the question is P equal to T. So the aim of the rest of the talk is going to be, okay, so first, perhaps let me explain. So my impression from the set theorists is the few remaining questions about the classical invariants that had survived the invention of forcing were gradually shown one by one to be independent of CFC by more and more elaborate forcing arguments. And sort of this was left, and it was expected, as I understand it, that eventually there would be a forcing argument showing that in certain cases they could be different. But the answer turns out to be that they're the same in CFC. And the interesting picture of why is because the combinatorial core of this question turns out to be the same as the combinatorial core of a question in model theory, and they both have CFC solutions. So this is what I want to say just a little bit about. Okay, so now mean, while, and model.
So for example, T and B can be different?
Yes, my impression is T and B can be different. So in fact, so there are, okay, so maybe I'll just say there's something called John's diagram. So there was some beautiful work of so Kellner and Goldstern, Kellner, Shelah, Neisha, perhaps in various combinations. So there's a diagram of perhaps 10 of the classical cardinals, and one question is, once you start to know all the binary relations between them, then you can ask, can you have a model in which all 10 of them are different, whatever. And there start to be all sorts of interesting questions about these things. And people have a lot to say about that. So like I said, this is just, this starts to be really interesting for set theory once you have forcing.
By the way, why are they called invariants?
So this is a good question. So they have many names, and again, so I will give you my opinion as a model theorist, and set theorists might say something different. So one thing they're called is cardinal characteristics, which is also a nice name. So you could certainly complain, why are we calling them invariants? Because their size could change, right?
What are they invariant under?
Oh, so they're sizes of yeah, externally defined sizes of certain families, which I suppose it's okay. It's a good question whether one should call them invariant or not. So maybe that we should discuss at coffee, but it raises a good question, right? Which I will say, which is that asserting that they're equal is certainly not saying that we know what their size is. So here, when I'm saying they're equal, I'm not saying we know it's LF1 or we know it's LF2 or we know it's LF5. I'm just saying whatever model of set theory we're in, whatever value this takes, this also takes.
So it could be independent of the actual size.
The actual size can certainly change.
And when
You
you
know that it can change, or you think that it can change?
We know it can change.
and when you say of the continuum, it means they are similar in invariant or whatever for all the cardinals.
Oh, this is a great question. So there's so we can mention, for example, Gary Fisher has a lot of work. So you could try to define, P for a cardinal kappa that isn't necessarily the continuum, T for a cardinal kappa, and people have lots of very nice results about these things also. Yes.
So in your example, they are all linearly ordered, kind of as a consequence of ZFC.
Yes.
So is this a general picture, or do you have some of them that are just?
There are all sorts of interesting things that can happen. So these particular ones happen to be linearly ordered, but there are lots of others that there are lots of others that continue to be invented constantly. So people are sitting around in this term. They might, they have some cardinal invariants they want to define, thinking maybe coming from optimality, but there could be some more. Okay. All right. So meanwhile, in model theory, so let's call this 2. Saturation of ultrapowers. And Keisler's order. Okay, so now, although they are suggestively close to each other on the board, now we move to a completely different world. And this is comparing complexity of theories in model theory. Now,
Sorry, theory means a language and a set of axioms.
yes, exactly. So let me say, for example, we have the set of axioms saying am an algebraically closed field of characteristic 0, or I'm an infinite random graph. So the axioms for this say there are infinitely many elements, and for any n, there's an axiom saying if there are two disjoint sets of size n, there's somebody connected to everyone here and not to anyone there. You could say I'm a real closed field. You could say I'm a linear order. I'm a dense linear order with no endpoints. Okay, so over here in this world, we're saying something like, is an algebraically closed field more complicated than an infinite random graph? And the way we're trying to figure that out is we're quantifying over not only all infinite cardinals, but all regular ultrafilters and all infinite cardinals. So the questions.
What does it mean?
Well, thank you. I will say this in just a moment, but just to set the stage, the objects we're comparing are different, and the scale on which we're comparing them is also completely different. Okay.
When you start with the theories,
Yeah.
you assume that every closed formula is full of overs.
Yes, it's a complete, yes, thanks. So these are complete. So in fact, I should say not only complete, but also countable. So countable theories means the language is countable, so the number of sentences is countable. You could make sense of this for bigger theories, but already the interesting case seems to be where they're, yes, and they're complete, so you've made a decision about every. Okay. So let me remind you what an ultrafilter and an ultrapower is. Okay, so ultrafilters and ultrapowers. Okay, so an ultrafilter, let's say, is a notion of largeness. So we have a set X, and an ultrafilter, it's a collection of subsets of X with the following properties. So the whole set, okay, so I'm going to colloquially say, I'm going to say that a set is in the ultrafilter if it's large. I'm going to use the word large to describe elements of the ultrafilter, which is a point of view. Okay, so the whole set is large. The empty set is not large. If some set is large and we have some superset of it, then the superset is also large. If two sets are large, called A and B, then their intersection is large. So by induction, the intersection of any finitely many is large. And the ultra part is that we make a decision about everybody. So for any subset of X, exactly one of A or the complement of A belongs to F, and not both, because if both belonged, then the intersection would get to the Okay, so this is you've made a decision for every possible subset of X as to whether or not it's small or large in some coherent way. So notice that, model theory is going to think about the class of all models satisfying the same set of sentences. So it's very useful to be able to build more models, and ultrafilters give you a way to do that. So let's give an example. I'm going to define ultrapowers by example. So let's take the natural numbers considered as a linearly ordered set, and let's build its ultrapowers. So we're going to take some set I, for example, the natural numbers, and we're going to take D, an ultrafilter I. So first I have to tell you what the base set is. So I look at the Cartesian power and the I. So this is my I indexed tuples. So I'm going to draw the ultrapower like this. Here are all of my copies of n indexed by I. Now, here's my I. So here is my formless Cartesian power up here. Notice anytime I take an element of the Cartesian power and I take another element of the Cartesian power, there's a set on which they're different right? And a set in which they're the same. And that partitions I into two pieces, the set in which they're the same, the set in which they're different. And the ultrafilter has an opinion about which set is big. So if the ultrafilter says most of the time they're the same, we declare them to be the same. If the ultrafilter says most of the time they're different, we declare them to be different. This is an equivalence relation because ultrafilters are closed under finite intersection. So the actual set we get is a reduced power. It's we identify two infinite sequences precisely if they're the same on the set the ultrafilter thinks is big. And so the elements of our model are these equivalence classes. And now if we want to be able to reason about it before we do anything else, we pick a representative of each equivalence class. And then we show that, then it's not difficult, but it requires some thought to show that what we get at the end doesn't depend on the choice of representative. Okay, so now we've got this ultrapower. We have the elements of the ultrapower, which are these equivalence classes, and we have a representative of each class, and that's useful because it means that if I take an element of the ultrapower, and the I and the D, and I take an element of the index set, which is T, and I say, what is the value of A at T? Well, it's an equivalence class, so that doesn't make sense, but I picked a representative, and so this actually has a value. Okay, so now I can reason about this. And the point is that any structure that I have defined on every single element of the class now naturally extends to the ultrapower. So for example, I take two elements of the ultrapower, let's use the same sequence of X's and O's, but now I ask a different question. I have a linear order defined at every factor. So here I say, is X bigger? Yes, here they're the same, here they're the same, here X is bigger, here X is bigger, here X is smaller, here X is bigger. So I divide into two sets, the set in which is bigger, the set in which it's not bigger. The ultrafilter thinks one of them is big. And so I declare this to be bigger than this if most of the time it's bigger, right? So I could also have used, if I had addition, I could have defined addition. If I had multiplication, I could have defined multiplication. Basically, anything that's a relation function or constant, anything that comes in the language of model theory that is well defined in every factor, I can extend naturally to the ultrapower. So I get something else at the same kind. Okay, but I don't just get something else at the same kind unless my ultrafilter is trivial. I would get lots of other things. Okay, so it's an exercise in this case to show that the equivalence class of 0 is really the first element, and the equivalence class of 1 is really the next biggest thing to the equivalence class of 0. So I get a copy of n on this linearly ordered set in the ultrapower, but I also have the equivalence classes of things that get bigger and bigger and bigger, and the equivalence classes of things that are bigger than them. Notice that this is no longer a well-ordered set because it's still going to be true that in this ultrapower, there's exactly one element with no predecessor, which is the first one. All right, so when I take this ultrapower, I get a much, much, much bigger linear order with the first element and the last element. Okay, so how is this going to help me compare theories? So, all right, so so Keisler's order. So I'll write this down. It's not necessary to parse everything here, but let me give you a definition for completeness. So we have T1, T2, complete optical theories. And we say that T1 is less than or equal to T2 if every infinite cardinal for every regular ultrafilter D on lambda, for every model of the first theory and model of the second theory, if the second ultrapower is lambda plus saturated, then the first ultrapower is lambda plus saturated. So there are a couple of words missing here. So what is regular? So regular means that, so it's an extension of non-principal. I'll just say it means there's a family of sets, all of which you think are large. the number of them is the same as the index set of the filter, and the intersection of any finitely many of them is still in the filter by definition of filter, but the intersection of any infinitely many of them is empty. So it's a generalization of non-principal, which is the right generalization to higher sets. And what it means in this context is if you restrict your ultrafilters to being regular, which consistently all ultrafilters are regular, so it's a very natural condition, then this entails that in this particular definition, the choice of model doesn't matter. It's really about the elementary classes. So this part of the statement will hold for some equivalently every model of T1 and some equivalently every model of T2. But you can pick whichever model makes your calculation easier. You'll get the same answer. Okay, so what about saturated?
How important is it that you've quantified overall lambda?
That's a very good question. So at the end, right, once you know the structure of Keisler's order, then it wouldn't mention ultrafilters and it shouldn't, you should be able to say, okay, here are the however many classes and here are the lambdas you need. But for now, a priori, we don't know anything at all about which lambdas you need. We don't even have an upper bound. We don't know that it's absolute.
So minus what saturated means again?
Okay, yes.
Or we need to remember that.
No, I will, this is, okay, so let me say this next. So saturated means, okay, so what is lambda plus saturated? It means that, so you're in a model M and you have set A of parameters and maybe I shouldn't, okay, so the usual letter for types is P. Now, this is obviously not a good letter to use for types in this context because it means something completely different, but it's a very difficult reflex to get over. So, okay, Q of X is a type over A, which means some set of formulas. Some set of formulas in the three variable X with parameters from A, which is finitely consistent. Any finitely many of them have a common solution, and you're asking, does the whole thing have a common solution? So let me just try to give you a very simple example of how this would compare. So let's compare algebraically closed fields and linear orders. So here are our algebraically closed fields. Here's our index set I. We're going to do the same ultrapower of two different things. So here we have our linear orders. Get the linear order here. Okay. So we have the same lambda, the same ultrafilter and lambda. A type in the algebraically closed field, well, you could say it's algebraically closed, so it will realize anything saying I'm a root of some polynomial. So maybe an interesting thing would be to pick a field, subfield K of size lambda, and to write down a set of conditions saying you're transcendental over it. Okay. So I'm not a root of any of these polynomials with coefficients in K. So Q1x says transcendental over K. What would a good example of a type in the linear order be? It would be you have kappa many elements going up and kappa many elements going down, and you're saying I'm in that cut. So what kind of questions should you imagine the ultrapower is asking? So at a high level, what the ultrapower is doing is something like it's choosing finitely many of the formulas, and it's choosing a particular value, and it's returning to you the projections of those finitely many formulas of the value. So you should think about that as the formulas remain the same, but you have no control over what the coefficients look like. So if we're in an algebraically closed field and somebody gives us finitely many polynomials and they give us a particular algebraically closed field that we used in our product and they say, in this field, is there somebody which is not the root of any of these finitely many polynomials? The answer is always yes. So we can always solve that problem. And because we can solve all of those finite subproblems, there will be somebody transcendental here. But in the linear order, somebody gives us finitely many intervals, and they give us a particular projection. And all we know here is that we have finitely many intervals. We have no guarantee that they're consecutive, no guarantee that they have any kind of intersection or overlap. And we want to find a common solution. It's now much harder. Just taking finitely many intervals where we know nothing about their endpoints, there's no reason they should have a common solution. So this is a much harder problem. You need the ultrafilter to contain many, many more sets to be able to arrange things, on average, any two of them are concentric, but at a particular projection, they don't necessarily have to.
Is it clear that you need to move to another surface, or is it possible that you can distinguish the two theories without going to another surface?
I suppose the question is how you want to distinguish them. So, for example, stability that we talked about in the first talk, algebraically closed fields are a very stable theory, linear orders are a very unstable theory. So if you just want to count types, for example, that's a reasonable measure of complexity, and that will show you a difference between the two of them. Without ultrafilters. Yeah. Okay, but maybe this is a good point to mention. So at the end of the first talk, I'd asked the question, stability and instability it's a very nice division within theories, and you happen to find it because you try to look at this particular counting function. There might be all sorts of other ways of distinguishing the vast collection of other theories. How do you see the interesting divisions there? So one of the things that I think is powerful about ultrafilters, one of the reasons I was interested also in working in this problem, is that it allows you to see stability, but it also, in principle, allows you to see many, many, many other divisions. This is a more general point of view. If your theory is a stable theory, then because of these indiscernible sequences, because of these large sets of elements that look alike, basically there's only one way they grow in ultrapowers. So there's a very natural sense in which the stable theories are kind of a special case of disorder where everything grows in one direction, and then the rest of the map now is something you can try to study. But the thing about the ultrafilters is maybe to make a personal comment, that's sort of what the ultrafilters are doing. You're not looking for a particular kind of complexity. You're asking for the ultrafilters to tell you what they see as the same and what they see as different. And ultrafilters are very forgiving. There's this infinite set, and there could be an infinite set where things look one way and an infinite set where things look the other way. If ultrafilters think things are different, it's because it has to be a very, very, very strong signal. Anything can be up to finite error, up to small error.
We know of theories that cannot be distinguished at all unless using an ultrafilter.
So there are advances in our understanding of how to distinguish things using ultrafilters that are kind of going ahead of the rest of model theory, so we don't yet have good model theoretic explanations.
But there could be a theorem saying that if you can distinguish two theories via an ultrafilter, you could distinguish them without.
That would be great, because what you would really like to do is use this as a tool to find divisions.
So this can be true, such a theorem.
It would be great. It would be great. In fact, I think one of the reasons that Keisler's order was sort of stalled for a long time is people thought it was some very complicated set theoretic question that was about the ultrafilters and not about the theories. And so the thing I had proved when I first started thinking about it was that this thing about Keisler's order is really local, it really depends on formulas. The reason I was thinking about this is I wanted to understand for myself, is this something about theories? Is this something that at the end won't be about ultrafilters? Okay, so we don't have a theorem to that effect because we don't know the end. It ends up being a much bigger and deeper problem than perhaps it seemed initially, but
I'm confused about type. So you take a subset of the model
Yes.
and each of those elements.
You're allowed to use it as a parameter, yes. So it's a kind of,
Which kind of subset? Can you take them, all of them, or you start with what
So-
you get?
so think about it as being kind of completeness. But you don't have any kind of a metric, you just have a very weak topology. So you want to ask the question, maybe a type is a kind of limit point of a model. So you look at all of the definable sets and you ask the question, is there a collection of definable sets with the property that any finitely many of them are consistent, but there isn't actually an element that simultaneously satisfies all of them. Now, once you do that, you have to add in some measure of size, because you could take, for every element of the model, you could take the set saying, I'm not equal to this element. And then there's never somebody satisfying all of them. So you would never get the answer that you're complete. So what you do is you make the size smaller than the size of the model. So you
just
fix,
that.
yes, just that. Now, so in this case, there's a quantification, there's a cardinal somewhere here. Where did we put it? So there's a size, and this size is the size of the ultrapower, and you ask, do you have completeness up to that size? Basically, that's what you're asking.
That's what this lambda
Yes,
plus.
that's what lambda plus, yes. Lambda plus says, if you give me a set of parameters of size less than this, so less than or equal to lambda, then anything you can describe by that exists. Great. Okay, so I have a few minutes, so let me just say a couple of things about what happens. So we have this notion of saturation. We have this question of comparing theories according to how saturated their ultrapowers are. And so the punchline is, okay, so we were trying to understand the maximal class. Okay, so Keisler had defined this order. He had proved there's a minimum class. He had proved there's a maximum class. His maximum class involved a lot of coding. It was something very much like piano arithmetic. That was in the 60s. Shelah had proved in the 70s in classification theory two very important things for our story. First, that the stable theories are visible in this context. They're the first two classes are exactly the stable theories. But he had also proved that in the class of maximally complicated theories, you have the linear orders. So because of various things that happened since then, we were trying to ask the question. So here's, just so it's on the board, I'll write this here, is SOP2 maximal in Keisler's order. So let me not define this now. I can define it in T if anyone's interested. So this is a particular kind of tree. So this was a question, or perhaps we turned it into a question about comparing orders in trees in ultrapowers. So you know linear order is maximal, and you want to know if this particular kind of tree is maximal. So you're trying to say, we look from very, very far away in our ultrapowers, we look at the trees, we look at the linear orders, we look at whether or not we realize cuts, we look at whether or not there are paths through trees. Do those gaps happen at the same time? And so perhaps I'll just write down over here so you can define. If you want to compare how ultrafilters deal with trees and orders, the name is completely by analogy at this point. You could define P of D, a cardinal invariant of an ultrafilter, say, or cardinal associated to an ultrafilter, is the smallest kappa, so that for some P regular ultrafilter on lambda, what's the smallest kappa, so that for some infinite linear order x, if you look at the ultrapower x to the lambda mod d, there is an increasing sequence of length kappa 1. So let me call it a kappa 1, kappa 2 cut. So you have your linear order, and there's an increasing sequence indexed by kappa 1, a decreasing sequence indexed by kappa 2. It's describing a cut, which is unfilled. And because we want to make this into a size, we measure the cut by taking the max of the size of each side. Okay, so P of D is the smallest kappa, so that you're trying to measure the ultrafilter using a linear order. You take this linear order, you look at the ultrapower, you ask what is the smallest size of the cut, and you flatten it into a measurement, which gives you a single number, right? When you add infinite cardinals, you just take the max. Okay, and you could also ask T of D. So this is the smallest kappa, so that for some tree T, so a tree for me is a partially ordered set with the property that the predecessors of any node are well ordered. Take some tree and you look at the ultrapower of the tree. There is a kappa indexed path with no upper bound. So here we should ask, okay, so here probably the most important thing I can describe is what direction I draw my trees. So if I have a tree like this, I take the ultrapower, I get a much, much, much bigger partially ordered set. And a way of measuring what kinds of gaps exist in trees is to ask, if I take some path through the tree, what's the shortest walk I can take along a path so that there's no upper bound. Okay, so this is something I can measure about ultrafilters using trees. This is something I can measure about ultrafilters using linear orders. And so the point is, we had figured out that if we could show that, okay, so because linear order is maximal, if you can see a hole in anything, you can see a hole in linear orders. So P of D is less than or equal to T of D. Now, if we could show that they were equal, then we would be saying that if you can see a hole using trees, then you can already see a hole using linear orders, which would somehow tell you, I mean, this is saying that the complexity of trees and the complexity of linear orders are the same from this point of view. And so it would answer this question that we were interested in. But it turns out, so I won't explain maybe this in great detail now, but I'm happy to say more at tea or any other time if people are interested. The interesting thing is that if you go back and you look at the question of P and T, you can also see that in something very much like a regular ultrapower, you can define, so a generic ultrapower, so something that looks very much like a regular ultrapower, but that you see in a forcing extension. You can also see that there's a measurement of this ultrapower using linear orders and a measure of the ultrapower-like structure using trees. And if it were the case that P was less than T, then you would have the measurement having to do with linear orders is less than the actual P, is less than the actual T, is less than the measurement having to do with trees. So at this point, the reduction is, if you could show on general grounds that anytime you had an ultrapower-like structure in which you had a collection of orders and a collection of trees, and you had a measurement of where the gaps in the orders are, and you had a measurement of where the gaps in the trees are, if you could show in ZFC that these two measurements always had to be the same, then you would show that P has to be equal to T always, and you would show that SOP2 has to be maximal, that the trees and the linear orders and ultrapowers have to be the same always. And so that's what the proof does. It shows that in an ultrapower-like structure, your measurement of where the gap in the order is and where the gap in the tree is have to occur at the same place. So perhaps that's where the model theory really shines, because you're trying to say something about how certain families of types interact together and have a similar level of complexity. Okay, so I will be happy to say much more about that.
So this is your theorem.
This is the, well, with Shelah, right? This is our, so this, the main theorem of the paper from the maybe from the paper's point of view, the main theorem is that in ultra-power-like context, which we call the cofinality spectrum problems, the measurement of trees and the measurement of orders are the same. But what the paper does is it says one example of that is this question, and one example of that is the T question. And so once you reduce to that, then you get both of those as a consequence in CFC.
And once you know that there is no pure set theoretic.
Yes, the set theorists. So the set theorists have many interesting and short proofs of this, but somehow, despite this, the model theoretic proof seems to still be interesting and useful for people. I mean, it says something about these cardinals are describing phenomena which goes beyond this particular manifestation, and it leads to lots of other interesting questions. So, so for example, you can do them for other infinite cardinals. You can also ask the question, what other classes in this order have interpretations as cardinals, right? So what's really nice is there starts to be this kind of land bridge, and things talk to each other. But yes, there were lots of interesting things people did with this proof, both just to check it for themselves and also to give other descriptions. More questions?
I have slow sometimes, so once again the definition of regular. Some intersection has to be empty, but I don't remember.
Okay, so when you have an ultrafilter, okay, so you have all of these sets which are big, the only thing the definition of ultrafilter tells you is if you take finitely many of them, the intersection is still big. But that's like seeing the surface of the ocean, and you have all the waves underneath of the more complicated intersections that you don't know about. So regular is saying that there's some family of sets and their size is the same as the size of this, and they're very, very spread out. And the definition is for any element T, it only belongs to finitely many of them. That's what's saying that you can't find infinitely many of them with non-empty intersection. So equivalently, any T belongs to only finitely many of them. So you can imagine that, let's think about ultrafilters on the natural numbers. So suppose I have everything but 0, everything but 1, everything but 2, everything but 3, and so forth. So this is an infinite family. Is it a family of this kind? No, because I could take the infinite subfamily consisting of everybody except the set emitting 2, and that would have intersection 2. So there are lots and lots of families that do not have this property. But if I had taken the family, everybody but 0 of the co-initial segments, then they have this property that any infinitely many of them have. So if you want families like this that are very, very spread out to exist in larger sizes, you make this assumption of regular. And the reason is that model theoretically, they tell you that all of the problems you're thinking about really didn't have infinitely much information all the way along. So this is what model theory is. That's its bread and butter, right? Speaking about the finite. Yes.
Could also record the definition of lambda plus.
Saturated. Yes.
No. It's lambda plus. But what does lambda plus?
Oh, it's the next biggest infinite size to lambda.
Ah.
So this is just a shorthand after yes. Yes.
So it seems not obvious from the definition that the Keisler order is reflexive.
Okay, yes. So it's a pre-order in theories that maybe we think about as by reflexive you mean for a single T.
Yeah.
Okay, so that's what regular is doing for you. Yes. So regular is telling you that it's also not a partial order, it's a pre-order in theories and spoken about as a partial order in the equivalence classes. But yes, so when Keisler defined Keisler's order, he proved that if E is regular, then if you have two models that are elementarily equivalent, let's say in a countable language, otherwise you have to say language of size less than or equal to lambda, then and the lambda mod D is lambda plus saturated. So say T countable, say lambda plus saturated, if and only if n prime of D is lambda plus saturated. And so it doesn't matter what model you pick in the elementary class. Now, we can, because we drew this picture of regular, so the point is somehow that if you have lambda many conditions in the ultrapower and you're trying to figure out if you can satisfy them all at once, you assign each one of these to each one of them to one of the sets in the regularizing family, and you only consider it when you're in a T belonging to that set. And that tells you you've only assigned finitely many formulas to worry about in each place. And you can do that in a way that still means everybody's considered on a large set.
So we can prove this at home.
Yes. And so if you didn't have a family like this, then you might have, imagine that you've got the rationals as a linear order, and you have your ultrapower. Let's just say this is an ultrapower countable set. And I don't know, you want to realize the cut at pi. So just try to use Walsh's theorem, the fundamental theorem of ultraproducts. Okay, what's the set in which this interval has a common solution? Everything. How about this interval? Everything. How about this interval? Everything. Okay, so here I am at this index, and I want to simultaneously realize, all of the elements describing a cut at pi. I can't, because it doesn't exist there, right? So I can't just say assign everybody to a set of which it has a solution, because then I point out a failure of saturation at my original thing. But if I use the non-principality to say, okay, solve some of them here and some of them here and some of them here, then I could build a solution. So it's just distributing things in a way that allows you to realize them without needing the index models themselves to have any saturation.
So this comparison of theories, does it tell you about probability in this theory? Does it, somehow, if one theory is bigger or in this order than another, then, I don't know, you can import proofs of theorems in one to prove theorems in the other.
So that's an interesting question. So, okay, so let me interpret the question as, okay, so you could say that maybe one theory is interpretable in another theory. I mean, you could try to define a much tighter connection where you say something like, is there a theory that interprets both of them? And so is there a direct way of translating structure in one to structure in the other? So you can define orders like this, and they will be weak. They will refine Keisler's order. But maybe the interesting thing about the ultrapowers is that it allows you to compare things that in principle have nothing to do with each other. Okay, so let's compare algebraically closed fields and random graphs and linear orders that we started with, right? So the algebraically closed fields are minimal, the random graphs are in between, and the linear orders are maximal, and all of these are theorems. And they have no interpretation in each other, right? So at least a reason it seems like it might be pretty interesting is it's telling you something about maybe average behavior, whatever that means, but not in a way that requires them to be talking about the same thing.
So it's more about their sizes.
Yes. So size is the first stage when you're talking about stability, and then there are other kinds of finite growth rates. So this
It's
is
about growth rates. It's not about the theorem thing.
yeah, as far as we. Okay.
There are no other questions. So thank Maryanthe again.